This telescope will take blurrier pictures than Hubble. And yet, astronomers say it could change astronomy more than Hubble ever did. Sounds absurd, right? Telescopes are supposed to be judged by how crisp their images are. How could something fuzzy reveal more? Actually, it is exactly what's happening. And almost no one outside astronomy circles is talking about this $1 billion machine that will make it possible, a new Vera Rubin observatory in the Quimbo region of Chile. This thing is about to begin the biggest revolution in sky watching, and yet it's somehow flying under the radar. You see, the Vera Rubin Observatory is built with quite an ambitious purpose in mind, to create the most complete time-lapse of the universe we've ever attempted. And it has already started to make fantastic images and groundbreaking discoveries. So, what makes Rubin so special? And why are astronomers calling it the telescope that will change everything? First off, how is this new telescope different from other big players? Everyone knows Hubble for its breathtaking beauty shots. And now, James Webb dazzles us with razor-sharp close-ups of galaxies at the edge of time. But the Vera C. Rubin Observatory plays a completely different game. It isn't about sharpness. In fact, its pictures will look blurrier than Hubble since the observatory is taking them through the Earth's atmosphere. And that sounds like a flaw until you realize it's by design. Hubble stays deep at one patch of sky. Webb zooms in on faint galaxies so distant they are almost invisible. Rubin, on the other hand, is built to see everything at once. To cover such a wide field, it can't afford pin-sharp resolution. The trade-off is clear. You give up some detail in exchange for a movie of the entire sky. Rubin carries the largest digital camera ever built for astronomy, 3.2 gigapixels. It weighs 3 tons and has the size of a small car. And each exposure of this beauty is so massive that if you tried to display it on a 4K TV, you'd need hundreds of screens tiled together just to see the full image. The telescope itself is a 350-ton giant with an 8.4-meter mirror, and its field of view is staggering. One shot covers an area of sky the size of 40 full moons. Hubble, by comparison, would barely fit a grain of rice on that plate. And this wide-image machine is relentless. Rubin will scan the entire southern sky every 3 nights. Imagine building a complete scrapbook of the heavens and updating it again and again and again, night after night, year after year. That means data, and more than you can imagine. Hubble collects about 8 terabytes a year. James Webb around 200 terabytes a year. Rubin, 20 terabytes every single night. That's the equivalent of millions of high-res photos dumped into the archive before breakfast. And astronomers won't just store this avalanche. They'll comb through it in real time. Alerts will go out within 60 seconds whenever something in the sky changes. A supernova flares, a rogue asteroid appears. Scientists around the globe will know almost instantly. So, James Webb is the world's most powerful microscope, zooming into cosmic cells at unimaginable scales. Hubble is a master photographer, snapping iconic portraits of the heavens. But Rubin is the ultimate dash cam of the sky, running a time-lapse of the entire universe, catching every flare, every collision, every transient event we might otherwise miss. And there's a poetic symmetry here. The observatory is named after Vera Cooper Rubin, the astronomer who first provided compelling evidence for dark matter back in the 1970s. She noticed that galaxies were rotating far too fast for their visible matter to hold them together, meaning something invisible, some unseen mass had to be there. Her work fundamentally reshaped cosmology. And now, decades later, the telescope carrying her name is about to give us the most powerful data set ever to test those mysteries. And that's why astronomers are losing sleep over this machine. Not because it will give us the sharpest images, but because it will give us all the images fast enough and wide enough to finally see the universe as a story unfolding in real time. And we already have some glimpses into what this observatory is capable of. This image is called the Cosmic Treasure Chest, Rubin Observatory's very first proof that this machine is not just powerful, it's pure spectacle. What you're looking at is a deep, expansive image of the southern region of the Virgo cluster stitched together from 1,100 exposures captured over just 7 nights, all to create a 24-square-degree sweep of the sky, roughly 20 times the area of the full moon. And in that frame alone, you're seeing about 10 million galaxies, just 0.05% of the 20 billion galaxies Rubin will survey over its 10-year mission. Every dot of light is a galaxy with hundreds of billions of stars. What once looked like empty space is suddenly crowded with spirals, ellipticals, dwarfs, and faint background smudges stretching into the deep. Here's what leaps out: those bright flecks of red, blue, and yellow. They reveal age, distance, even temperature. Bright spirals glowing blue with newborn stars, giant ellipticals burning amber with ancient ones. You can even spot a triple merger tucked among the glittering crowd. 3 galaxies caught in the act of colliding, their stars weaving together in a gravitational ballet. And if you look even closer, the faintest smudges in the background aren't noise. They're entire galaxy clusters so distant they barely whisper their light to us. But this treasure chest isn't all galaxies. There are also our own Milky Way stars. Those bright points are stellar neighbors who will be tracked over time to trace our galaxy's history, its streams, its hidden dwarf companions as they drift across the sky. That's already staggering. But Rubin wasn't done showing off. It turned its giant 3.2 gigapixel eye on 2 of the most iconic star-forming regions in the Milky Way, the Lagoon Nebula, known as M8, and the Trifid Nebula, aka M20, which are several thousand light-years away from Earth. The lagoon is a glowing cloud of gas and dust where massive young stars are carving cavities with their fierce radiation, sculpting the nebula into pillars and ridges. Rubin's wide-field view captures not just the central cluster, but the entire surrounding region, showing how newborn stars reshape their environments on colossal scales. Right next to it, the Trifid is even stranger, a 3-in-1 nebula. One part glows red as an emission nebula lit by hot stars. Another part shines blue as starlight scatters off dust, and dark lanes cut straight through the middle, dividing it into 3 sections. Within those dark clouds, stars are just beginning to form, their light still hidden from view. With Rubin's repeated observations, astronomers will be able to watch those stars brighten, flicker, and emerge over time, turning snapshots into an unfolding drama of stellar birth and creating a time-lapse of stellar life itself. 10 million galaxies, stellar nursery seen in exquisite detail, a sky so full of structure and life that it feels less like a static photograph and more like the frame of a movie. With Rubin, the universe is no longer still, it's alive. And while Rubin isn't fully online yet, even during test runs, it already made some outstanding discoveries. With asteroids, we're getting serious results fast. In just 10 hours of test observations, Rubin spotted more than 2,000 new asteroids. That's an instant world record, since other observatories, both ground and space-based, never found more than 20,000 asteroids per year. Rubin could easily cover this number in just 4 days of proper observations. And each detected asteroid might be a clue to the orbit history of the inner solar system or even a potential Earth threat. Rubin has already flagged some near-Earth objects, rocks whose paths cross ours, the ones we really want eyes on. These early alerts are critical for our survival in the long run. But here's the part that really made astronomers sit up. Rubin has already gone interstellar without even trying to. On July 3rd, 2025, it captured this faint dot that later turned out to be an interstellar object passing right through the solar system, 3I our Atlas. Prior to that, we've only found 2 others, Oumuamua in 2017 and Comet 2I Borisov in 2019. Now, thanks to Rubin's observations, astronomers calculated 3I our Atlas's orbit, and we got number 3. But those images also helped us understand what it actually is. Earlier estimates guessed that this is an asteroid as large as 20 kilometers across. But Rubin's data showed a clear coma, which means it's actually a comet that looks larger than it is. This way, astronomers pinned 3I our Atlas closer to 1.1 kilometers, still making it the largest interstellar object ever observed. The subsequent observations confirmed a bright coma and tail, settling the debate that this was not just a rock, but a genuine comet from another star system, a chunk of ice and dust that formed around another star, probably much older than the Sun, now sailing through our neighborhood. And Rubin was the first one to catch it in detail. Every pixel here helps us understand how other planetary systems build their comets and whether ours is anything like the rest of the galaxy. Speaking of other systems, in the same test runs, Rubin also started to map variable stars, so-called standard candles that change in a predictable way. By tracing them, astronomers can pinpoint cosmic distances and map the structure of the Milky Way itself, meaning that Rubin is already laying down the framework for a 3-dimensional map of our galaxy. So, let that all sink in. This observatory isn't even fully online yet, and it's already rewriting our catalogs, thousands of new asteroids, potentially hazardous objects flagged, a comet from another star system measured with unprecedented detail, stars charted across the Milky Way. And this is only the beginning. When the Vera C. Rubin Observatory fires up its full survey, it will try answering the universe's most mysterious riddles, starting with dark matter. Yes, the very elusive substance that Vera Rubin herself helped discover back in the day. Now, the observatory named after her will be able to trace the invisible web of dark matter masses by mapping weak gravitational lensing across billions of galaxies. This will paint a cosmic scaffolding in 3 dimensions, letting us watch how galaxies cluster and line up over cosmic time. When we see dark matter structures more clearly, it will definitely help theoretical physicists narrow down the specific theory about its origins and mechanics. Then there's dark energy, the force that's stretching the universe apart from the very beginning of time. For decades, we've assumed it a constant, a static push coming from space itself that accelerates its expansion. But new results from the dark energy spectroscopic instrument are shaking that assumption to its core. DESI mapped 15 million galaxies and quasars, creating the largest 3D survey of its kind. And when its data was combined with cosmic microwave background maps, supernova measurements, and weak lensing studies, a strange pattern emerged. Dark energy's influence appears to be weakening over time. Scientists are now almost certain in that weird evolution, enough to say it's more than a fluke, even if it's not a slam-dunk discovery yet. If true, it means dark energy isn't a fixed constant, but a shifting force. This possibility rewrites everything. It challenges the standard lambda-CDM model of cosmology, the one built on a constant dark energy, and injects uncertainty into the ultimate fate of the universe. Will expansion continue forever, slow down, or even reverse? Rubin will step into that mystery with a power play. It's able to observe hundreds of thousands of supernovae every year as precise distance markers while mapping weak lensing patterns at insane resolution. It will be the experimental backbone needed to test whether dark energy evolves or holds steady after all. And at the same time, thanks to that crazy wide lens, Rubin will catalog millions of asteroids, providing an unprecedented inventory of near-Earth objects. What about detecting new interstellar visitors? Well, at this point, it's essentially guaranteed that Rubin will spot some and will go from just 3 to 10 in a matter of years. And in our own galactic backyard, Rubin will perform Milky Way archaeology. With more than 20 billion stars mapped and positioned in motion, we'll reconstruct our galaxy's history, revealing ancient collisions, shredded dwarf galaxies, and stellar streams tracing cosmic mergers. But even after that, there's a place for the biggest thrill, the unknown unknowns. Every great observatory has revealed the unexpected. Hubble discovered dark energy. Webb showed us magnificent early galaxies. And Rubin, with its all-sky time-lapse, is poised to reveal whatever surprises the universe still hide from us in plain sight. And we've already had a taste. Astronomers using the Atacama Large Millimeter Array in Chile just reported a strange radio source in the nearby galaxy NGC 4945. This thing, nicknamed Punctum, is very compact and extremely powerful but only visible in millimeter wavelengths. A feeding black hole, you might think, but astronomers didn't find any signs of necessary X-ray emissions. Moreover, the polarization of Punctum's radio waves doesn't make any sense. It doesn't look like a pulsar or magnetar or whatever we know so far. Still, it's right there, posing a mystery that we aren't able to solve with our current knowledge. And although the Vera C. Rubin Observatory can't catch radio light per se, Punctum is exactly the kind of mystery it is built to find, not once in a while, but constantly. It's only fitting that this machine carries Vera Rubin's name. She revealed dark matter by looking at galaxies differently, overturning what we thought we knew. Now, her namesake observatory will do the same for the whole 21st century. So the next time you read the headline, astronomers found something inexplicable out there, chances are Vera Rubin caught it first.